sure. Okay, so as I was saying earlier, in this section we're going to do some special factoring cases, and these are basically cases where you have like a formula to do all the work for you. All these cases are going to be the reverse of special products, and so you'll recognize like difference of squares and things like that. In the next chapter, we're just going to go over like general strategies for factoring all sorts of stuff. So you'll see examples picked from the first 4 chapters combined. And so we'll do a bunch of different examples. Should be all sorts of fun. All right. So recall that we have a special product that says a plus or minus b squared is equal to a squared plus or minus 2ab plus b. What we're about to do, we're going to learn the reverse of that special product, and so instead of thinking it going this way, we're actually going to think about it going the other way for a change. So first of all, let's go ahead and take it from the a plus b squared to the right side with a couple of examples, just to outline what we're doing here. So this guy here, x minus 5 squared, when we FOIL everything out, notice that we have our a squared, because our a was equal to x in this particular, actually maybe I'll just say here, a minus b squared. And so our b is 5, our a is x. So a squared, that's our first term. Our second term is 2 times b, which is 5, times a, which was x. And then our last term is b squared again. Once we put it all together, we get x squared minus 10x plus 25. The same thing is true about this lower one, x plus 5 squared instead of x minus 5 squared. Notice it's the same exact thing, just with a plus sign here instead of a minus sign. But once again, we have 2 times ab plus b squared. All right, so if they wanted us to go in the reverse order, they want us to factor this guy, all we need to do is determine it's of the form a squared plus or minus 2ab plus b squared. And this one's a minus, so this would have to be minus 2ab plus b squared. This one, I can rewrite it like I've done in this middle step here. Right? If our a is x and our b is the square root of 16, square root of 16 is 4. So right here in the middle, you can see that I can write this as 4 times x times 2 out here in front. So that's 2 times a times b. The last term I can rewrite as 4 squared. So this one conforms to the formula. All right, and so if my a was x and my b was 4, this is just x minus 4 in here.
Why are we square rooting 16?
That's just, so I write it that way because this is the way the formula has us. Yeah, and so you don't have to necessarily do that, but you got to keep it in mind that you're squaring that term. And of course, the square root of 16 goes right here where the b is, and so it helps us to take the square root immediately. So that is more or less like how you use the perfect square trinomials, and we'll do a bunch more in just a second. So, so for a trinomial to be in the class of perfect squares, like we did with the last example, it's got to conform to this one. So you've got to be able to rewrite it in terms just like this. It helps to just kind of make a little list on the side of your paper to check if this is in fact a perfect square trinomial. So once again, a squared in this example, in example 1, x would equal a, because we have a squared out here in front. B squared would have to be back here, so what would b? What would b be? 3, exactly, right? 3 squared equals 9, so that's what b is. Now, let's do the calculation. 2 times a times b. 2 times x times 3. Well, that's equal to 6x. Now we go back and we check it with our middle term. Our middle term is in fact 6x, so yes, this is a perfect square. If we wanted to finish this guy out real quick, we would say, oh, there's a plus sign there, so that means there's going to be a plus sign in my binomial. So a plus b, which b is equal to 3 squared. All right, so for this next one, t squared minus 8t minus 9. What is my a in this example? T. Right, the first term is a squared. A can't be anything else besides t in this example. What about my b? Is there, whoops, is there a square root of negative 9? You can't, right? Yeah, negative times a negative is a positive. Positive times a positive is another positive, right? You can't square something to get a negative 9 unless you're in the realm of imaginary numbers, which you guys don't want to go there yet. So, b, we can say there is no b. So no, this does not conform to a perfect square trinomial, right? If you can't say there's a square at the end, you can't say this is a perfect square trinomial. And so we don't even have to go to the step 2ab.
That's because you can't split.
You can't take the square root of the 9. Yeah, that's where it really comes down to. And so it's like when you have that a squared plus 2ab plus b squared, you know, you just take your first and last terms and say, can I take the square root of that? If you can't, then this isn't a perfect square trinomial. That doesn't mean you can't factor it. That just means you can't use this formula to factor it. All right, this next one, this is a little bit different. So for this one, we can rewrite this guy. I can rewrite this as 4x in parentheses squared minus 56x plus 7 squared. That makes sense? I just swapped these guys around just in case we missed that. Swap those guys around and rewrote 49 as 7 squared. So our a is 4x, our b is 7, 2ab is 2 times 4x times 7, which is equal to 56.
You line up the formula, and then it just lines up.
Oops, 56x. Sorry, what was that, Ed?
When you line up the formula on top of the 4x2 from 56x, just brings it down.
Yeah, I mean, you're really just rewriting what you kind of rewrote up here.
The formula breaks it down.
Oh, you.
A2 plus 2ab.
Yeah.
If you put it right on top.
Exactly, yeah, if you put one over the other, it would look pretty similar, right? And then you just have to break this middle guy down a bit. So now that we confirmed that 2ab does in fact equal a version of the middle term, we got to notice real quick that the middle term's negative though, which means that our negative in the middle of our binomial, or sorry, the sign in the middle of our binomial will have to be negative as well. So this guy, of course, is equal to a plus b squared, except for we're using the negative version of this. And so over here, we're going to have a, which is 4x, minus b, which is 7 squared, and we're good. All right, so we'll do some more examples here. This is kind of the, whoops, and of course, as we saw earlier, I screwed this up. This is supposed to be a minus right here. All right, so that's kind of like this is your official rule. You could go ahead and write that on a note card before the exam if you want, and it's totally cool. All right, so this next guy here, x squared plus 6x plus 9. Let's check to see if it's a perfect square. So our a would equal x. Our b would have to be the square root of the last term, which in this case is 3. 2 times a times b, well, that's equal to 2 times x times 3, which is equal to 6x, which is the middle term, so we're good. So we can just write this right away. We can say a plus b, a is x, b is 3 squared. All right, so this guy, number 2 here.
How did you write the formula?
Oh.
How are you?
And so the formula we used on that example was this guy up here. Okay. And you guys all might want to write that down real quick because we're going to be using it throughout the class. You'll want to be able to kind of check to see what I'm doing. All right. So this guy here, number 2. Once again, we're not really in an order that we like, so I'm just going to rewrite this guy in descending order. We have t squared minus 14t plus 49. All right. So we have an a that equals t. We have a b that equals the square root of this last term, which is 7. So 2ab, that is equal to 2 times t times 7, which is equal to 14t. And so yes, we have a perfect square trinomial here. Notice real quick that the sign is negative, so we're going to be using the negative version of the formula, which is the one on the bottom up here. So this guy, if a is equal to t and b is equal to 7, then we have a minus b, t minus 7 squared. All right, so this guy here, number 3, we have 100x squared minus 180x plus 81. Does 100x squared have a square root? Does 100 have a square root? 10. Yeah, x squared clearly has a square root because it's squared. So we can rewrite this guy, or we can outline our a's and our b's, I guess. So a is equal to 10x, b is equal to square root of the last term, which is 9, 2ab, that's equal to 2 times 10x times 9, which is equal to 180x. So yes, we have a perfect square trinomial. We're going to notice that the sign is negative, so we're going to use the negative version of the formula. That is right up here somewhere. That again is this last is the last line up here with the blue underneath it. Yeah.
So b equals 9 is 9 is the square root of
9 is the square root of 81, right? And so a is always the square root of the first term. B is always the square root of the second term. If one of those terms doesn't have a square root, then you don't have a perfect square trinomial, and you got to factor through other means. And so 2ab, that's what has to equal the middle term, right? If 2ab doesn't equal that middle term, once again, you don't have a perfect square trinomial. All right, so we use the negative version of the formula, and the negative version of the formula tells us that this equals a minus b squared. So our a is 10x, our b is 9, and we square it. And so this would be our final answer. Sorry, it's getting a little crowded up here. Okay. So we can also have the case where we have multiple variables where it turns out to be a perfect square trinomial. For this one, we do the same thing, right? We say, okay, a, which is equal to the square root of 9p squared. So that's equal to 3p. Does that make sense? I'm just kind of doing one extra step in there. Yeah, so a is equal to the square root of the first term. B, that's equal to the square root of the last term, which is going to be the square root of 4x squared. That is equal to 2x. And then we're going to just make sure that this is a perfect square trinomial by calculating 2ab real quick. And so this is 2 times 3p times 2x. So that's going to give us 12xp, or px. So yes, that is the middle term, so we're safe to use this formula. We notice that we have a plus sign here, so we'll use the positive version of this formula. So this guy is just equal to a plus b squared. A is 3p, b is 2x squared. So you can see that, you know, I mean, if you kind of get used to this little format, like this makes stuff pretty easy if you recognize it as a perfect square. All right. So for this last example, first step of any factoring, if we have a common term, we want to factor it out. In this one, we have a common term of x, and we also don't really like to have a negative on our leading term, so we're going to factor out a negative with that. So this guy, we're going to factor out a negative x, and that's going to give us an x squared plus 24x plus 144. All right, so now we're going to factor this inner polynomial real quick. And so to do that, we're going to check once again, since that's the section we're in, if this is a perfect square trinomial. So a, which is going to be the square root of the first term, that's x. B, which is going to be the square root of the last term, which is 12. And then let's check to make sure this is a perfect square trinomial. 2ab, that's equal to 2x times 12, which is 24x. And so yes, this is a perfect square trinomial. We'll notice it has a plus sign, so we're going to be using the positive version of the formula. We're not going to forget our x that we factored out earlier. So the positive version of the formula says a plus b squared. A is x, b is 12, and we square it, and we're done. How is everybody on those? They're okay? All right. All right, so a different kind of special factorization is the difference of squares. So basically, when we run into a polynomial that can be written in this form, then we have a difference of squares. Basically, that means you can take the square root of the first term and the square root of the second term, and there's a negative sign in the middle, and that's it. All right, so for a good example of this, right, we have x squared minus 9. This can be rewritten as x squared minus 3 squared. So let's go through and determine if these are if these qualify as difference of squares problems. So what's the square root of this first term? Yeah, a equals 3x. Is there a square of 264? 8? All right, there we go. So a is 3x, b is 8. Actually, I think at this point we're just supposed to be identifying these. So maybe I shouldn't take you too far. Since we haven't discussed the formula yet, we'll just be checking to see if these are perfect square trinomials. I don't want to jump too far ahead. What about this one? Number 2, we have 25 minus t squared. Is that a perfect square is that a difference of squares? Sorry. What do you guys think? Can we rewrite this as a difference of squares? Yeah, what can we rewrite 25 as? 5 squared minus t squared. There we go. A squared minus b squared. Sure, it conforms. This guy here. First of all, we're going to notice the negative term is sort of in the wrong order, so we're just going to rewrite this as 36 minus 4x to the 10th. Well, we know what the square root of 36 is, right? It's 6. The square root of 4x to the 10th, well, that is 2, times x to the 5th. Right? So yeah, we can rewrite that as a difference of squares, so that does conform, and we could use the formula we're about to learn on it. All right, so the actual formula that we're going to use is this guy here. A squared minus b squared equals a plus b times a minus b. All right, so for this first one, we're just going to rewrite this guy in its difference of squares form. So we have x squared minus 2 squared. So this must equal x minus 2 times x plus 2. All right, this guy down here. We can rewrite this as a difference of squares. This is 1 squared minus 3p squared. So if we follow our formula, this is just equal to 1 minus 3p times 1 plus 3p. And so notice here the variable does not have to be the first term. Doesn't really matter that much. All right, this guy here.
S3 squared.
There you go, exactly, right? S cubed squared minus, what's this guy going to turn into? 4 what? T to the 5th. Right, okay, so a minus b squared, well, I already know that's a difference of squares, so that just equals a minus b times a plus b. So it's s cubed minus 4t to the 5th times s cubed plus 4t to the 5th. There we go. All right.
25.
Not at first glance, right? We look at this and we say, well, 50 doesn't exactly have an even square root, but we know that half of 50 does. 25 has got an even square root, so let's just try and factor some stuff out first and see if we can mess with it after that. We'll notice that we have at least an x squared in each term, and we have at least a factor of 2 in each term. So we're going to factor out 2x squared. What we have left is 25 minus 4x to the 6th. All right, we can rewrite this as a difference of squares. So this is 2x times 5 squared minus 2x cubed quantity squared. All right, so that means we just get to use our formula where a is equal to 5 and b is equal to 2x cubed. So we don't forget our factor out front. We have 2x cubed, and then on the inside we're going to have 5 minus 2x cubed and 5 plus 2x cubed. Whoops, this one outside should be a squared, sorry. All right, so remember this guy. This is one of those super common mistakes. This is definitely not equal. right? The 2 doesn't distribute, the exponent doesn't really distribute over that addition or addition or subtraction sign. All right. Factoring completely. So sometimes there's a little bit more to do even though you've factored once or twice. Sometimes even after you've factored 3 times, there's still a little bit more to do. First thing we'll notice about this example is that it is a difference of squares, and so we can write this y squared minus 4 squared. This splits up, according to the formula, into y squared minus 4 and y squared plus 4. Now we'll notice real quick that this is also a difference of squares. It's just inside parentheses, that's all. So we're allowed to break that down one more time. We're not just allowed to, we're required to. So, okay, so we have y squared minus 2 squared. So that splits up again into y minus 2 times y plus 2. And then this guy cannot be factored anymore. Okay, so just because you factored once and it worked real nice and clean doesn't mean you're done. You got to check each and every one of these to make sure that it's prime. All right, so let's go on to section 5.5. So in this section, we're going to just do a bunch of different factoring examples. You know, it's been kind of easy to choose out the method up to this point because we're in that specific chapter where the method is presented, but we're no longer doing that. So now we're going to need kind of more of a general factoring strategy. The book outlines a pretty general factoring, a pretty good a pretty decent strategy on page 366. You know, it's definitely a pretty good one to have. And if you're uneasy with factoring, like, you know, you might just want to make a copy of it, put it next to you when you do your first 5 or 6 homework assignments, and then try and move on and do it without. So basically, what these instructions say is look for a common factor, and then part B says you look at the number of terms, and the number of terms will tell you which special factorization you should check for. So if there's 2 terms, obviously you want to see if they're both squares of something. If there's 3 terms, you want to go through the motions of checking for a perfect square trinomial. If it's neither of these, then you're going to try using sort of the reverse FOIL or the grouping, or, you know, whatever method you can come up with after that. After you've come up with a method that's appropriate, you factor completely, and then part D, you always want to check your answer, even though I don't do that in front of class very often. Do as I say, not as I do. All right, so suppose we ran into this guy. Well, we would say, okay, step 1, are there any common factors? No, clearly there's not, right? So then we'd move on to step 2, and we'd say, which method do we want to use? Is it possible that this is a difference of squares?
Yes.
You're thinking perfect square trinomial. It's possible it's a perfect square trinomial, but not a difference of squares, because a difference of squares only has 2 terms, right? Yeah, it's that a squared minus b squared. And if you really think about what difference of squares mean, that'll help you to remember what the formula is. So no, it can't be a difference of squares, but yeah, it's possible that it could be a perfect square trinomial. So let's just check that real quick. So if it were, then my a would be the square root of the first term, which is x. My b would be the square root of the last term, which would be 10. 2ab, well, that's equal to 2 times x times 10, and that's 20x. So yes, this is a perfect square trinomial, which means I can use that formula to figure out what the factorization is. So step 3, we go ahead and implement that formula. X plus 100. And so this guy says that this should be equal to a minus b quantity squared. So our a is x, our b is 10, and we square it. And remember, we put a negative here because there was a negative out here. If there was a positive out there, it would be a positive inside the brackets. All right, step 4, we check it out. We'll do this one just because it's so much fun. And so with this one, it is 10 minus x times, whoops, sorry, x minus 10, x minus 10. And so we just FOIL it out if we really want to check this guy. So we have x squared, we have minus 10x, we have another minus 10x, and then for our final term, we have a plus 100. And yes, this is correct. We did this correctly. Cha-ching.
Would the 20x be squared?
In the middle here?
Because the 10x and 10x.
No, remember when we use addition or subtraction to combine x's, nothing happens with that variable term. We just add it. You know, it's like saying negative 10 apples minus 10 more apples. It's still apples, right? If that probably doesn't make a whole lot of sense, but all right.
Sorry, I forgot.
It's all good. There's a lot of rules here. It's perfectly normal to forget a bunch of them. I do all the time. All right, so this guy here, step 1. We're going to factor out any common terms. Does it look like there are any common terms here? Common factors, I should say, not common terms. Nope. There are none, right? So we go to step 2. We want to determine if this conforms to a special factorization. There's not 2 terms, so it can't be a difference of squares. There's not 3 terms, there's 4, right? So it can't be a perfect square trinomial because those are always 3 terms. And we can't combine any of these either. So we can say, well, maybe I'll do this with reverse FOIL, but then we notice that there's 4 terms, which usually indicates factor by grouping. So we're going to try that out and see if it works. So we have, oops, I'll go down to step 3 here. So we have 2x cubed plus 10x squared is x plus 5. All right, so these first 2 terms, I'm going to factor everything I can out of them. It looks like I can factor a 2 because a 2 is contained in both of them, right? There's a 2 here and a 2 times 5 here. And there's also at least 2 factors of x contained in each one. So I'm going to factor out a 2x squared. 2x squared. What do I have left? Well, that is x plus 5. And I know I'm on the right track now. I'll go ahead and write this out first. I know I'm on the right track now because I have 2 matching factors, x plus 5 and x plus 5. Real quick, I'm going to write this with a 1 outside of it, so I know what gets left behind. That's a really frequent mistake with this when you don't have any like coefficient out front, is you just assume that x plus 5 goes away. All right, so we're going to pull out our x plus 5, and then we write in what's left, right? And this 1 right here remains because we had a 1 coefficient right here. All right. Then we want to check our work. We can do that by just foiling this guy out real quick, which is an exercise left for later maybe. All right. So now let's move on to this next one. This is a little weird looking. Step 1, let's factor out some common factors. First of all, we don't like that we have a bunch of negative numbers here, so we know that we're at least going to factor out a -1. What's the largest number, what's the largest degree of x I can factor out of all three of these terms? X cubed, right? All right. Excuse me, I'm going to cough today. All right, so I'm going to factor out a -x cubed from all these terms. So this first one becomes an x squared. The second term becomes a positive 14x. And the last one becomes a positive 49. All right. So it certainly looks like, as we go to step 2 here, it certainly looks like I have something worthy of the old perfect square trinomial in the middle here. It's got 3 terms. The last one has a square root. The first one has a square root. Let's go ahead and check it out to make sure it conforms. So if this were a perfect square trinomial, then a would have to be the square root of the first term, which is x. B would have to equal the square root of the last term, which is 7. And let's check what 2ab is just to make sure it's a perfect square trinomial. So 2 times a times b, that's equal to 14x. That is the middle term, so yeah, this is a perfect square trinomial. The middle term's positive, so we have to use the positive version of the formula. Let's go ahead and factor this guy completely. -x cubed. The perfect square trinomial formula says that this guy must equal a plus b quantity squared. So I have a, which is equal to x, b, which is equal to 7, and I square it and call it a day. Step 4. I have written here that you guys should check this out. It's a typo, I like that. Please multiply this guy out and make sure I didn't screw anything up. Right, and so this would have to equal, make sure that it equals -x to the 5th minus 14x to the 4. All right, do I have any confirmations? Thumbs up, awesome. All right, make sure you guys do these when I ask you to. Don't be like me and let your logical, lazy brain 2 rest on the work of others, because that's not going to work for you in a test. That works fine for me because I don't have to take any tests anymore. All right. Here are some more examples. This one says to factor completely. What I'm going to notice right off the bat is that I have terms I have factors of x and y in all 3 of these terms. And it also looks like I have at least a factor of 3 in all 3 of these terms. So I'm going to find what I can factor out here. And so let's see now. We have an x squared in at least every term. We also have at least a y to the 4th in every term. All right, 3 would be the other thing that we can factor out of every term. So I'm going to go ahead and write that guy out front. So 3 x squared y to the 4th. Then I'm just going to see what's left. So 6x squared y to the fourth. When I take an x squared, a y to the fourth, and a 3 out of that, all I have left is a 2. 21 x to the third, y to the fifth. When I factor a 3x squared y to the fourth out of that one, I get a negative 7xy. And for this last guy, I factored the 3 out, so there won't be a coefficient. I factored all the x squares out, so that's going to go away. And I factored 4 of the y's out, so we have a y squared left. All right, I'm just going to rewrite this guy real quick in descending order on the inside here, so we can sort of have this looking a little more like we like it. 3x squared, y to the fourth, y squared minus 7xy plus 2. Okay. So now what we want to think about real quick, we want to say, what the heck does this look like when we factor it? So usually we can write this stuff out, right? And so usually we can say, well, this is equal to 3x squared y to the fourth times 2, here, I'm going to write it down below. So usually we can say this is equal to 3x squared y to the fourth, and then we can split up this inner polynomial into what we think the factors are going to be. And it's usually pretty easy to do that. Whoops, that shouldn't say equals. So y squared, okay, we know what we're doing there. So we're going to have at least a y up here. Our last term is just a single digit, which means in our second terms of our binomials, those are both just single digits without any variables. But our middle term contains an x. That's not possible. So it's prime. And it's a little bit weird. It'll take you a while to get used to seeing that and realizing, oh, that's just not possible. But after a little bit of practice, it'll come pretty quick. That, yeah, there's no way to make up this middle term with an x in it if this last term does not have that x in it. So this one, the final factorization of this one occurs just right after we pull out that first factor. All right. So, and make sure you take a little bit of time to make sure that this isn't prime, right? It's important that, you know, like you don't just say, well, I can't see an immediate solution, so that's got to be prime, right? No, you're going to mess yourself up doing that. You'll lose a lot of points on the test if you stop there when that wasn't prime. Okay, let's check out this next one, number 2 here. So it looks like we have some common factors. Each of these terms contains factors of a and b, so we're going to take the smallest available, or the largest factor contained in all of them out. So we can definitely take out a b, right, because there's a b contained in every term, at least one of them. And we can take out, it looks like we can take out an a squared, because there's at least 2 factors of a in each term. So we're going to do that to start this problem out. Okay, when we factor a squared b out of this first term, we get an a squared b squared. We factor a squared b out of this second term, we get a 2a, whoops, we get a 2a, that's it. Oh, right, I only had a single b, sorry, I was confusing myself there. Yeah, only a single b, so yeah, we have an ab in the middle. Okay. So this last term, when we factor out an a squared b, we get a negative 15, and that's it. Okay, so now we've factored out our common term. We have to go about factoring this polynomial in the middle. We can rewrite this guy real quick as AB squared plus 2AB minus 15. Okay, so now we know that our factorization is going to look something like this. A squared B, since this is the squared term, that's what gets split up. AB, AB. All right, we have a negative back here, but a positive back here, or up here. So this has got to be two positives if it's anything. Oh, sorry. No. One's positive, one's negative. Yeah. Okay, but the larger factor gets attached to the positive. We'll know that at least. Yeah, and I think you guys can already see it, right? You know, if we wanted to, we could build out our table and we could write factors of 15 right here and their corresponding sums over here. You know, if we wanted to do that, sorry, negative 15, we would say like negative 1, positive 15. That equals, when you combine them, that equals only 14. That's bad. We didn't want that. Then, of course, there is negative 5 and positive 3. That equals negative 2. But we wanted a positive 2, so that's not it. Positive 5, negative 3. That equals positive 2. So those are the factors we want to use. Negative 3, positive 5, and we're good. All right. So when you guys do this stuff on a test, you know, you'll definitely want to put like some sort of intermediate step in here, like, or even on your homework, especially with this one, it's not that important, but I was just thinking about it for the special products and stuff. You'll want to make sure you tell me that, like, you know, if it's a difference of squares, write it as a difference of squares before you use the formula. Does that make sense? That was kind of off topic, but so, like, you know, if you have, let's say, t squared minus 4, I want you to rewrite this real quick, even though it's very obvious where you're going to go with it. I want you to rewrite this as t squared minus 2 squared. And then you just use the formula, t minus 2 times t plus 2. And that's fine, just as long as I get that one intermediate step that shows, you know, you knew what you were doing. Nope. Nope, that's fine. No, you don't have to prove anything like that to me. You know, so don't just state it's prime, though, if you can't figure it out necessarily. Like, you know, yeah. I mean, you could. It doesn't really matter. All right, so this next guy. So once again, we have two variables, and we have a negative on our first term. Don't really like that, so we're going to go ahead and factor a negative out of this guy right off the bat. So we have 10m squared plus mn minus 3n squared. All right, so when we break this guy down, we notice that we have an m squared and an n squared, which means this is going to break down kind of like this. We're going to have two m's. Whoops. I'm going to leave room, actually. We're going to have an m up here, an m right here, and then we're going to have an n here and here. And there's still going to be numbers in front of these. But we know basically how that's going to split up. So we want to go about factoring this guy out. When we take a look at this, we can see that, let's see now, so we're going to need to use one of those methods that we hate, right? When we have a coefficient, we have factors for our n term. So what we do first is we say, what are the possible factors of our leading coefficient, 10? So we say, this is going to look like this. It's got to either be 1m times 10m, or it's got to be 2m times 5m, right? Because those are the only two sets of factors of 10 that possibly could work. Okay, now we're going to start considering factors of the negative 3n squared. Factors of that are stuff like negative 1n times 3n, positive 1n times negative 3n. All right, so now remember the brute force method. We basically just plug all these factors in to each one of these guys in forward order and reverse order. So let's start with 2m and 5m. And I'm only starting with that because I know that's what the answer is. You know, otherwise you'd have to start, you know, wherever you, kind of like wherever you thought the answer might be. You know, sometimes it becomes obvious with certain problems, but you'll get the hang of it. So, okay, so we got to try these guys out. So 2m minus 1n, let's try this upper set of factors first, plus 3n. If we did that, what would our two middle terms be? So we would have, our first term would be 10m squared, just like we would expect. Our middle term, sorry, our O term will be 2m times 3n, so that is 6mn. Our I term would be negative 5mn. Then our last term would, of course, be just like we knew it would be, 3n squared. All right, when we combine these guys, we get 10m squared plus mn minus 3n squared. So that's the one we're looking for. It was this guy. It's convenient. That was the first one we did. So now, all we got to do is go back up to the first part of the problem and make sure we didn't miss any factors. We almost did. We almost missed this negative here. So we're going to go down and we're going to write out our final factorization. We're going to say negative 2m minus n times 5m plus 3n. And then we're done. All right. How about this guy? So for this guy, once again, there's only two terms, right? But you can't factor a common term out of both of them, so we're going to move on from that step, and now we're going to consider special factorizations. There's two terms, so we have to say, well, does this have a square root, and does this have a square root? Can this be rewritten as a difference of squares? Yeah, it totally can, right? Because these are 4s, so obviously, you know, if you can take, basically, if you can take the degree of the leading coefficient and it's even, it's got a square root, right? So we can rewrite this as a squared, b squared, squared, minus 4 squared. And so the formula says a squared minus b squared is equal to a minus b, a plus b. So we just need to rewrite this guy as ab squared minus 4 times ab squared plus 4. Are we done? Can we factor either one of these further? Totally, right? Yeah, the one on the left. Yeah, because there is a square root of that, obviously, because it's squared, and there is a square root of that. It's 2. So we're going to apply this rule one more time. So this is equal to ab minus 2 times ab plus 2. And then this guy is prime, so he just stays there. ab squared plus 4. And there we go. That's the final factorization. Alrighty. So for this guy, step one is always check to see if there are any common terms we can factor out. There are no common terms in this one. Step two, this is not a difference of squares because it doesn't have two terms. So we're going to see if it conforms to the a squared plus 2ab plus b squared. Does it? Is there a square root of 12? Not an even one, so we're not going to do that. So it looks like we're going to attack this guy by just a traditional reverse FOIL guess and check. So this first term, we can rewrite this as xy, the product squared, plus 7xy plus 12. So that means this guy's going to split up as so. xy, xy. We have a positive here, which means they're both positive or both negative. We have a positive here, which means they're both positive. So what two factors of 12 sum to 7? 3 and 4. There we go. Right, and once again, all we did to figure out what those were, we said, what two factors of this last number combine to equal this middle number? And that was it. All right, let's move on to another one. So this guy here, excuse me. So for this guy here, we've already factored out a negative, it looks like, but I don't think we're quite done. We look at each term, we see that each term contains at least one x. This front term doesn't have a coefficient, so we really can't factor anything else out besides that x. So right off the bat, we're just going to do that. So we have a negative x on the outside, and that gives us x to the fourth plus 7x squared minus 18. Now, we're not so used to seeing a 4 and a 2 here, right? We're used to seeing a 2 and a 1 there. But we can rewrite this so there is a 2 and a 1 there. Just like this. So I'm going to rewrite this as x squared, there's our 2, plus 7x squared to the 1 minus 18. And so we go ahead and factor this guy just as we would if we had, like, you know, some x squared here. And so this is going to split up as negative x, and then we're going to have x squared multiplied by x squared plus or minus some stuff. So now, just like usual, we have a negative on the 18, so that means we're going to go ahead and write in a plus and a minus. We're going to do that right now because there's no coefficients out front, and so it's not dangerous to throw your plus and minus in right away. So, what two factors of 18, this last term, differ by 7? 2 and 9, right? If we, you know, and you can just go through the factors in your head. You say, well, factors at 18, well, 1 and 18, those clearly don't differ by 7. The only two other options are 9 and 2. Those clearly do, so it's got to be some combination of those. So the 7's positive, which means the 9's got to go on the larger factor. 9 has to be attached to the positive, and the 2 gets attached to the negative. And there we go. So if this were a different number than 2, if this were a number with an even square root, we would definitely factor this guy one more time. Since 2 doesn't really have an even square root, we're not going to worry about that at this point in the class. X plus 9, that doesn't have a square root. That's a prime. And in fact, just for a little, just something that might save you some time later, x plus any number a, x squared plus any number a is prime if a is positive, okay? x plus 1, x plus 10, x plus a million, x plus any number, it's prime. Just the way it works. All right. So in summary, so now we're on 5.5. We're going to go to 5.6 next. We've been over all the different factoring types, right? There's the type where you factor a common factor out of each term in a polynomial. There's the kind when you have the so-called easy version without any coefficient out front. You know, the best way to handle that is usually with reverse FOIL. We've got the weird trinomials, the difficult versions when we have a coefficient out front. You know, that can be handled with a lot of different things, perfect square trinomials, and then of course the brute force method. I know you guys love that one. And then there's the sort of the special factorizations. So the next thing in this class, we're going to start doing this to solve polynomials. Kind of like what that looks like is if you have, let's say, x squared, and this is sort of just to prime you for what we're going to learn in the next class. This won't be on the homework or anything like that. Suppose we have x squared plus, let's say it's 5x plus 6. And that is equal to 0, right? That's something we haven't seen yet, this stuff in an equation. So what we can do is factor this guy, and we can say, well, if we factor this out, this is equal to x plus 3 times x plus 2, and that's still equal to 0. Then what we do is we recall a rule that we learned quite some time ago. That rule is if we have a times b equal to 0, then either a must equal 0 or b must equal 0 or both. We use that to solve each one of these factors for x. And so we say, well, a's got to equal 0 or b's got to equal 0. So we say, what if a was equal to 0? X plus 3 equals 0. And then over here we could say, well, what if b was equal to 0? X plus 2 equals 0. We solve this guy, and we get x equals -3. We solve this guy, and we get x equals -2. These are the solutions to this polynomial. Don't worry about it if that's weird. It's supposed to be, right? This is one of those things where I'm trying to introduce you to this stuff before we actually get to the lecture, and it's super crazy. But this isn't actually that bad, right? Like if you know how to factor this stuff, you could do it whether you know the concept or not. If you know how to factor, you just factor, solve each little factorization for 0, and you got the solutions. It doesn't matter if you understand this conceptually, but this is what we're going to be using in the next few chapters. All right, so thank you for your patience. Once again, the homework that was supposed to be due today is not due today. It's due next Tuesday, so if you want to take some extra time on it, please do. If you already turned it in, go ahead and dig it out if you want, or just leave it in there. So